In this video, we will be going over logarithmic functions. So recall that the graph of an exponential function such as f of x equals 2 to the x will look the following way. This time, let's plot the inverse of this function. We obtain the inverse by interchanging the x and y coordinates. So we can plot these new points, and then we draw a smooth curve running through them. A function and its inverse has this general property where it is symmetrical about the line y equals x. So if we have a function f of x equals 2 to the x, then the equation of the inverse is as follows. First we replace f of x with y, so y equals 2 to the x. Then interchange x and y, so x equals 2 to the y. And then we solve for y. But how do we solve for y when it is in the exponent? This leads us to a special type of function known as logarithms. So if a is greater than 0, and a is not equal to 1, and x is greater than 0, then for every real number y, x equals a to the y just means y equals log base a of x, and vice versa. So this means that we can rewrite exponential equations as logarithms, and log is the abbreviation we use for logarithm. This definition of a logarithm should be memorized. So the relationship between the logarithmic form of an equation and the exponential form of an equation is one that has many uses. Notice the relationship of the two forms. We can see that the value of the logarithm is an exponent, and we call a the base, and it is written as a subscript in the log form. And log base a of x is the power to which we raise a by to get x. So much of our work with logarithms involves converting between logarithmic and exponential notation. Let's try a few examples of how we convert between the two forms. We can write the definition of a log on the side so we can see how to convert between the two forms. Start with writing down the base, and the exponent will be the value of the logarithm, so 2, and then this will equal the log input of 36. And now the logarithm is converted to exponential form. We do the same thing for the next example, so starting with the base, and then the exponent will be the value of the logarithm, so -3, and this will equal the log input of 1 over 64. And the same follows for the last example. So start with the base, and then the exponent will be the value of the logarithm, so 0, which then equals the log input of 1. Let's also try a few examples of converting from exponential form to logarithmic form. We can start by writing out the word log, and then our base of the equation in exponential form will be the base of the log, so we have log base 10. The input of the log will be what the exponential expression equals to, so 10,000. And then this will equal the exponent of the base, so 4. And now the exponential equation is converted to logarithmic form. We do the same thing for the next example. Starting with the base, this will be log base 9. The input of the log will be what the exponential expression equals to, so 1 over 81. And then this will equal the exponent of the base, so -2. The same follows for the last example. So starting with the base, this will be log base 8. The input of the log will be what the exponential expression equals to, so 8. And then this will equal the exponent of the base, which is 1. So once we are comfortable converting between the two forms, we will use this process for solving logarithmic equations. A logarithmic equation is an equation in which at least one term contains a logarithm. So let's go over how we solve logarithmic equations. To solve a logarithmic equation of the form log base a of b equals c, we write the equation in exponential form, so a raised to the c equals b, and solve for the variable. Note that a and b must be greater than 0. So always check to see if this condition holds. Let's do a few examples of solving logarithmic equations. First, notice that the base is greater than 0, so this condition is satisfied. And we will need the input of the log to be greater than 0, so we can write this on the side. And the next step is to rewrite this in exponential form. So this equation written in exponential form will be 10 raised to the third power equals x. And now we just solve for x. So this will equal 1,000, and since the value is greater than 0, 1,000 is our solution. For the next example, we need to make sure that the base is greater than 0, so we write this on the side. The input of the log is greater than 0, so this condition is satisfied. Now let's rewrite this in exponential form. This will be x squared equals 25. And now we solve for x. We can use the square root property to solve this by taking the square root of both sides. This cancels out the square on the left, and we have plus or minus 5 on the right. However, we need x to be greater than 0, therefore we do not include negative 5 as part of our solution. The solution set for this equation will just be 5. We do the same thing for the next example. Check to see that the base is greater than 0, which it is, and we need the input of the log to be greater than 0, so this means that we need x to be greater than negative 18 over 7. Now we can rewrite this in exponential form, so we have 3 to the fourth power equals 7x plus 18. And then we solve for x. This will then give us x equals 9. And since this value is greater than negative 18 over 7, this will be our solution set. For the last example, again we need to check that the base and input are greater than 0, which they are. Now we rewrite in exponential form, which gives us 2 to the x power equals 16. To solve this exponential equation, we need to rewrite both sides so that they have the same base. So we can rewrite 16 with a base of 2 as 2 to the fourth power. And now that we have the same base, we can set the exponents equal to each other. This then gives us x equals 4 as our solution. So often when working with logarithms, we are asked to evaluate them, or to find the value of the log. So let's do some examples where we evaluate some logarithms. To find the value for log base 3 of 9, we need to find the power to which we raise our base 3 by to get 9. So 3 raised to something equals 9. That value is 2, therefore the logarithm evaluates to 2. To evaluate log base 10 of 1 over 10, we need to find the power that we raised 10 by to get 1 over 10. That value will be negative 1, so the log evaluates to negative 1 since 10 raised to the negative 1 power is equal to 1 over 10. To evaluate log base 25 of 5, we need to find the power that we raised 25 by to get 5. That value will be 1 over 2, since this is the same as taking the square root of 25 in exponential form. Therefore, the log evaluates to 1 over 2. So since our number system is a base 10 system, logarithms to the base 10 are very widely used and are called common logarithms or common logs. So log base 10 of x can be written as log x without the base 10 written in. The base is assumed to be 10 when it is not written in. Let's do an example of solving a common log. So this logarithm is equivalent to log base 10 of 3x minus 8 equal to 1. We check to see that the base is greater than 0, and that the input of the log must be greater than 0, which means x has to be greater than 8 over 3. Now to solve this, we need to rewrite in exponential form. So we have 10 to the first power equals 3x minus 8. And then we solve for x. This will give us x equals 6, and since this value is greater than 8 over 3, this will be our solution. There are a couple of properties of logarithms that can simplify our work. If we have a is greater than 0 and a is not equal to 1, we know that when a base is raised to the 0 power, it is equal to 1. And if a base is raised to the power of 1, it is equal to itself. We can rewrite these statements in logarithmic form. The first statement can be written as log base a of 1 is equal to 0, and the second can be written as log base a of a equals 1. Therefore, we have the following log properties that can be useful to memorize. So let's try a couple of examples. For the first example, we can use the first log property since the input of the log is 1, and whenever the input of a log function is 1, the log evaluates to 0. So log base 12 of 1 equals 0. And for the second example, note that this is a common logarithm with a base of 10. We can use the second log property since the base and the input of the log are the same. When that happens, the log evaluates to 1. So log base 10 of 10 equals 1. And this can always be checked if we write it in exponential form.